Chapter 16, Current of Electricity, Part 1. Okay, in this section, we will be learning about moving charges, which is electricity. But before we start, you may want to pause the video to think about the answers to these two questions. Okay, so I'm going to go through the answers now. Metal is a good conductor of electricity because of its free moving electrons. Okay, this is true because in metals, the electrons are free to move around, and when we connect it to a battery, the electrons will actually move from one terminal, which is the negative terminal, to the positive terminal. So the answer is true. Okay, and then next, question number 2, the charge of an electron is 1 coulomb. This is actually false because the charge of an electron is actually 1.6 times 10 to the power minus 19 coulombs. Okay, you don't really need to know this number, but just need to know that 1 coulomb is not the same as 1 electron. Okay, 1 coulomb is actually made out of thousands of electrons. Okay, then in this first part, we will be zooming into electric current. Okay, so the learning outcomes are as follows. Okay, so what exactly is electric current? In the previous chapter, when we learned about static electricity, it's about non-moving charges. So whenever charges move, okay, it will actually form a current. So electric current is defined as the rate of flow of electric charges. It's actually how fast the charges are flowing through a point in 1 second. So there is a formula for it. Is I represents current equals to the amount of charge Q over T, the amount of charge per second. Okay, or we can remember the formula by this triangle, which is Q it. Okay, so the SI unit for current is ampere, or we can use coulombs per second. Okay, but usually we use amperes instead of coulombs per second. So what does a current of 10 ampere means? It simply means that every 1 second, there is 10 coulombs of charge passing through at that point in the conductor. Okay, so you can take a look at this. Okay, this is a simulation or a animated picture of current flowing. So you have all these circles are actually electrons. So there are electrons in the wires, in the batteries, in the light bulbs. Okay, and then once the electrons move, okay, we say that there is a current. Okay, and the current is always flowing from the plus side to the minus side, and the electrons is flowing in the opposite direction. But we'll talk about the directions later on. So if I want to measure the current, I just put instrument to measure how much charges is flowing through every 1 second in this circuit. Okay, so 1 coulomb is actually defined as the amount of charge when 1 ampere of current flows through for 1 second. Okay, so now let's look at some questions to apply the formula. You may pause the video now to think about the answers. Okay, I'm going to go through the answers now. If 30 coulombs of electric charge flow past a point in a wire in 2 minutes, what is the current? So I'm finding I. So the first step is I equals to Q over T. So the amount of charge Q is 30 coulombs, and the time 2 minutes, I need to change it to seconds. Okay, the SI units, which is 120 seconds. So it's 30 divided by 120 seconds, I get 0.25 ampere. Next question. The current in the lamp is 0.2 ampere. If the lamp is switched on for 2 hours, what is the total electric charge passing through it? So now I'm looking for electric charge. So I'm actually looking for Q. So Q is I times T. So my I is 0.2 ampere times time, 2 hours. Again, I need to change 2 hours into seconds, which is 7,200 seconds. So I get the total amount of electric charges is 1,440 coulombs. Okay, next. In 1 minute, 60 microcoulombs of charge pass through a point in a circuit. What is the current? So again, I'm looking for I. So I equals to Q over T. So now my Q is the amount of charge, 60 microcoulombs. Micro means times 10 to the power minus 6, your prefix, divided by 1 minute, which is 60 seconds. So you actually get 1 microampere. Okay, next work example. In figure 16.5, the switch has been closed for 0.5 hours and the current flowing in the circuit is 0.1 ampere. What is the total electric charge that has passed through the light bulb? So in this case, I am interested in Q, the electric charge. So Q equals to I times T. Okay, so where I have my I is 0.1 ampere and my time is 0.5 hours. Again, change it to seconds. 0.5 times 60 times 60. Get seconds, so I have 180 coulombs. Okay, then over here I have 3 questions. You may pause the video now to think about the answers to these 3 questions and whether they are true or false. Okay, I'm going to go through now. The first question, a battery is the source of charge in a circuit. The charge which flows through the circuit comes from the battery, originates in the battery. Okay, the answer to this is false. We have learned in the previous chapter of static electricity, every metal has charges in them. Every metal has positive charge, which comes from the protons, as well as negative charge, which comes from the electrons. So, in a circuit, the charges are already present in the wire and the light bulb, and in the battery, the charge doesn't come out of the battery. Okay, it is already present in the entire circuit. Okay, so the answer is false. Okay, next one. Okay, before I move on, let me share with you animation or a simulation. Okay, over here I have a circuit. You can see all these are actually the charges. So this is an open circuit because my switch is open. My charges are stationary. Okay, inside the wires, inside the light bulb, inside the battery. So at this point of time, if the charges are stationary, the rate of flow of charges will actually be 0. So I have an ammeter over here. So the ammeter rate is 0 ampere. Okay, but once when I close the switch, you will realize that the charges will start to move. It doesn't come out of the battery and then go back all the way to the battery. Okay, it's like a bicycle chain. The entire chains move along. Okay, so you don't see charges disappearing. If I have one charge coming out of the battery, one charge will go back into the battery. Okay, you can observe this. And immediately, can you see that immediately when I close the switch, okay, the light bulb will light up immediately, okay, because once I close the switch, it's like you stepping on your bicycle pedal, okay, the entire chain will start to move. And when the entire chains move, as long as the charges are flowing through the light bulb, the charges are moving through the light bulbs, the light bulb will light up immediately. And there is a rate of flow. There's how fast the charges are moving across it. In this case, it's 1 ampere. That means every 1 second, I have 1 coulomb of charge moving past this point. Okay, and you can observe that I can actually increase the voltage of the battery. We'll talk about voltage later on, but you can look at the speed or the rate of flow of the charges and the current. Okay, so over here you can see that the rate of flow of the charges is so much higher. It's 12 ampere. That means every 1 second I have 12 coulombs of charge passing by. Okay, so this you can take a look at how the speed of the charges moving that is related to the current. Okay, so as usual, this is 1.1 as compared to like 12 or 11.6. Okay, so then we go back to our questions. Okay, so just now you can see from the simulation that the battery is not the source of charge. Next question, the charge becomes used up as it flows through a circuit. The amount of charge which exits a light bulb is less than the amount entering it. So from just now, what you can see is false again. Okay, the charges doesn't get used up. It's like your entire bicycle chain. One charge move out of the battery, one charge will go into the battery. Okay, the entire chain just move along. Okay, the charges do not get used up. Okay, so this is false. And then for question number 3, charge flows through circuit at very high speed. This explains why the light bulb turns on immediately after the wall switch is flipped. This is false because just now, as you can see, even when my current is very, very slow or very, very low, like 0.9 ampere, okay, the charges are moving at a very slow speed. The current is very low, but the light bulb will still light up immediately. Okay, because as long as the charges move, okay, the light bulb will light up. And the charges are already all along the entire wire and the light bulb. So once you give it a pushing force, no matter how fast or how slow the charge moves, as long as it moves through the light bulb will light up immediately. So this is false. Okay, so the answer to all these 3 questions are false. Okay, let's move on. Okay, in physics, questions may sometimes ask you about conventional current flow as well as electron flow. Okay, in the past, when people study about physics, they actually thought that current flows from the positive terminal to the negative terminal. But later on, they realized that current is the result of electron flow, and electron flow is actually opposite from minus to plus. But in exam time, usually we will still stick back to the conventional current flow because a lot of theories and everything has been designed based on the conventional current flow. Okay, so for electron flow, every one of you know that electrons is negatively charged. And so you will have a battery over here. Okay, the short line actually represents negative terminal and the long line actually represents the positive terminal. So electrons are actually negative. So the electrons actually will come out from the negative terminal. Okay, it will not come out from the positive terminal. So for electron flow, it actually moves from the negative to the positive terminal like this. Okay, but on the other hand, conventional current, which is what we always taught before we know about electrons moving that causes current, we always assume that current is actually flowing out from the positive terminal all the way to the negative, which is exactly opposite of electron flow. Okay, and then you also need to know that there is 2 types of current. One where the direction of the current is always the same. For example, battery. Okay, we say that the current always flows out from the plus to the minus. It only flows in one direction. Okay, so we call it this is the direct current. Okay, it only flows in one direction. Okay, and then next, we also have another type. Okay, this shows the direction of the current flow. It only flows in one direction. Okay, and then there is another type called alternating current. You can see that the current one time flows from plus to minus, and then the other time it goes from minus to plus. Okay, so this is actually an alternating current. Okay, so it continuously reverses direction. One time from plus to minus, one time from minus to plus. Okay, this is called your AC. Okay, in short, alternating current. And the symbol for alternating current is like this. Okay, most of our power stations generate electricity in the form of AC, not direct current. Only battery provides direct current. So actually your wall sockets plugs, your wall sockets, electricity from the wall sockets which come from the power station are usually AC, not DC. Okay. Okay, next. So how do we measure electric current? We measure by using an ammeter or a multimeter. Okay, although there is a multimeter, but in the O-level syllabus, you will need to know how to use the ammeter. Okay, so an ammeter looks like this. Okay, with a letter A in the center. Okay, and you need to know that ammeter must always be connected in series. That means I must be in the same path as I must put my ammeter at the path, at the point where I want to measure what is the current. Okay, ammeter has very, very low resistance, so it doesn't block the current at all. The current can just flow through it easily. Okay, so it doesn't affect the reading, or it doesn't affect anything in the circuit when you put an ammeter in series, because your charges must flow through the wires in a series. Okay, and then just take note that for ammeter, there's positive and negative terminal. When we go to the science lab, you will experience it. Okay, the positive terminal of the ammeter must be connected to the positive terminal of the cell. Okay, then the other end will go to the negative terminal of the cell. If you don't do this, you will get the needle of the ammeter will deflect below 0. Okay, this is not good. So if you have that happening, just swap the terminals. Okay, like you can see over here, there's a negative part is connected to the negative part of the battery, and this positive part is connected to the positive part of the battery, which is over here. Okay, if it goes down to below 0, just swap the connections to the ammeter. Okay, I will skip this. Okay, so we go into summary. What is a current? A current is defined as rate of flow of charges. 3 ampere, which is the units for current, just means 3 coulombs of charge are passing through every 1 second. Okay, the formula is I equals to Q over T, amount of charge per second. Okay, or you can remember by the triangle QH. How do we measure current? We use an ammeter, and the ammeter must be connected in series. Ammeter has very little resistance. Okay, so it doesn't affect the current flow. Okay, direction of electron flow. Electrons is negative, so electrons will always flow from negative terminal to positive terminal. And then next, direction of conventional current is opposite of electron flows, which is from positive terminal to negative terminal. And meaning of direct current and alternating current, direct current only flows in one direction, usually batteries, and alternating current AC usually changes directions. 1 second it moves from positive to negative, and then the next time it moves from negative to positive. So it continuously reverses direction. Okay, and it's the current coming out from your power stations. Okay,